Hello, welcome back. We are going to continue our discussion of the North Atlantic Gyre, the most studied of all the ocean gyres. We've started our discussion by looking at the Gulf Stream and some of the early explorers who discovered the Gulf Stream. We are going to continue to look at how the Gulf Stream actually is formed. And today, right now, we're going to look specifically at the difference between western boundary currents and eastern boundary currents. And then later, we will get into a very important concept, that of vorticity. So this is a diagram showing you surface circulation in the ocean. It's a very simplified schematic of surface circulation where the warmer currents are colored red and the cooler surface currents are colored blue. Now, if we look at the North Atlantic Gyre, we see the Gulf Stream, and the Gulf Stream is colored red because it is a warmer surface current. And if we look over here on the other side of the North Atlantic Gyre, we see the Canary Current, which is the eastern boundary current, and it is blue because it is a cold current. Now we notice that if we look at all the different ocean basins, they have a very similar pattern. Over here in the North Pacific, we see the Kuroshio Current, which is our western boundary current, and it is a warm current transporting warm water from the equatorial region up to the North Pacific. And the current that we all know so well, the California Current, which is transporting cold water down along the coast of California. If we look down in the South Atlantic, we see that similarly, there is the warm western Brazil current transporting warm waters from the equatorial region down to the southern part of this gyre. And on the eastern side, we see the cold waters being transported by the Benguela current. Now, if we look over at the South Pacific, we see again a similar pattern where the East Australian Current is the western boundary current, transporting warm waters from the equatorial region down to the southern portion of this gyre. And over on the eastern side of the gyre, we see the Peru Current, which is also called the Humboldt Current. The Indian Ocean also has a gyre system that is cut in half here, but we do see the western boundary current, the Agulhas Current, bringing warm waters poleward, and on the other side, which is over on this side of the screen, we see the West Australian Current bringing the cold waters back equatorward. Now, this image is showing us sea surface temperature, and it also has, again, a simple schematic of our different gyres. So if we look again at our North Atlantic Gyre, which we're focusing on at the moment, we can see that the red, which is indicating warm surface waters, and yellow, which is also warmer surface waters, that these red and yellow surface waters are being transported poleward in the Gulf Stream on the western side of this gyre, and that the cooler polar waters are being transported down back towards the equator. These green colors here are indicating cold polar waters on the eastern boundary of this North Atlantic Gyre. Again, if we look over at the North Pacific Gyre, we see a similar pattern with those warm red waters being transported northward in the Kuroshio, and the cold waters being transported back down towards the equator in the California Current. The South Atlantic Gyre also has a similar pattern with the Brazil Current bringing warm waters down from the equator, and the Benguela Current bringing the cooler waters back up from the poles. If we look at the South Pacific, we again see the warm waters being transported poleward by the East Australian current and then being returned here, these green waters that are coming back up along the coast here in the Peru current or Humboldt current. The Indian Ocean gyres also showing us that we've got these warm waters coming down in the western side in the Angolas current over here and being transported back up. The cold polar waters are coming back up, although less drastic in the Indian Ocean on its eastern boundary. So if we look specifically at the North Atlantic gyre, we notice that it is made up of 4 interconnecting currents that have different flow characteristics and temperatures. So the first current that we've already been talking about is the Gulf Stream. And what we see right here are the winds. These are the trade winds that Ben Franklin and James Rennell were talking about as piling up, as bringing that water and piling it up on the coast of South America, so that we then had this strong pressure gradient that then fed and was the force to give us the Gulf Stream that moved those warm waters northward. So one thing that we notice in this diagram as well is that there are also winds at the top. These are the westerlies, and the westerlies we see also mirror the shape of our gyre, and so they are also pushing our gyre along. However, the gyre, of course, is not following the westerlies perfectly. It's turning a little bit to the right through our Ekman transport. And we see also that the Gulf Stream is very narrow, whereas over here on the eastern side, the Canary Current, we have multiple lines indicating that it is much more diffuse. It's much more wide and spread out. This diagram of the North Atlantic gyre is giving us these different numbers, and these numbers are what we call volume transport. So the values here, these values here, the units behind those are called Svedrips, named after Harold Svedrup. And Svedrips are equal to 10 to the 6th meters cubed per second. That's 1,000,000 cubic meters of water per second. So that is a volume, right? Meters cubed is a volume per second. So that's a volume transport of water. And if we look over here at the Gulf Stream, we see that the volume transport is very large. It's about 55 Svedrips, or 55 million cubic meters of water per second. However, over here on the eastern boundary in the Canary Current, it's only about 16 Svedrips, or 16 million cubic meters of water per second, which is less than a third of the transport that we're getting in the Gulf Stream. Another thing that we notice when we're looking at a western boundary current is that it has a very defined boundary. So even just looking at it visually in the satellite image right here, this photograph, we see right here, this is Cape Hatteras that we've already talked about, where the Gulf Stream breaks away from the coast, and we can see this very strong boundary indicating exactly where the Gulf Stream is. Now we also notice these clouds, and these clouds, of course, are forming because the Gulf Stream waters are very warm, and there are no clouds formed on the other portion of the water of the ocean over here where there is no Gulf Stream, because these waters are cold. And so we can see exactly where the Gulf Stream is going by this very sharp boundary. Another thing that we notice is the color of the water. The color of the water doesn't have very much green in it at all. However, the waters over here are very green, very productive. So the waters that are not in the Gulf Stream are very productive, whereas the Gulf Stream waters themselves are warm and very unproductive. So if we look at these different characteristics of our different boundaries, we see that western boundary currents, like the Gulf Stream, are narrow geographically. They're very narrow. They're also swift. They're fast. They're about 100 kilometers per day. They also have very large transport on the order of 50 Svedrips. And they have a very sharp boundary, and the waters are very depleted in nutrients. They're very unproductive waters. Eastern boundary currents, on the other hand, are the complete opposite. They are wide, geographically speaking. They're spread out over a much wider geographical area. They're slow. They're only about 10 kilometers per day, nowhere near the speeds that we have in our western boundary currents. And they have small transport, as we were noticing. They're only about 10 to 15 Svedrups. They also have a very diffuse boundary, not very well defined. And there's a lot of coastal upwelling in eastern boundary currents, as we're aware of in the California current and the Peru current. And they are very productive because of that. Western boundary currents, these narrow, deep, and fast, warm currents that occasionally form eddies. Though these include, in the North Atlantic Gyre, as we've been talking about, the Gulf Stream. In the North Pacific, the western boundary current is the Kuroshio current. In the South Atlantic, we have the Brazil current. In the South Pacific, we have the Eastern Australian current. And in the Indian Ocean, we have the Agulhas current. Eastern boundary currents, those cold, shallow, broad currents with poorly defined boundaries. As we saw in the North Atlantic, that is the Canary current. And as we are very familiar with, in the North Pacific, the California current is the eastern boundary current. In the South Atlantic, the eastern boundary current is the Benguela current. And in the South Atlantic, the eastern boundary current is the Peru or Humboldt current. And in the Indian Ocean, we have the West Australian current. If we look at the schematic, which shows us a way of looking at the North Atlantic Gyre as a vertical subsection, as a vertical cross-section, we see that the waters are going into the page here. That's going into the page, and then they're coming out of the page over here. So we're going around the whole North Atlantic in this diagram. On this side, we have the Gulf Stream, which, as we see, is fairly narrow and very deep, sometimes going all the way down to the seafloor. These waters are very warm and very strong and have very high volume transport. Now, as the waters return over here on the eastern side of the North Atlantic in the Canary Current, we see that the Canary Current is very broad and spread out, and it's not very deep. It's in fact very shallow. These waters are cold and weak and very productive. So we have very different characteristics between our western boundaries and our eastern boundaries in all of our ocean gyres. We are now going to get into some of the physics and some of the details about why these ocean gyres have such a difference between their western boundary currents and their eastern boundary currents.